My name is Teck Kiang. I work in the Institute for Applied Learning Science and Education Technology. It's a new research center set up by the National University of Singapore. Today I would like to share with you on this particular topic called Doubly Classified Models with R. Briefly, this afternoon I'm going to share with you on how to use R to carry out doubly classified models for contingency table. And this modeling approach in analyzing contingency table is quite rarely used in practice, and is really stated in the common statistical textbooks. And at most it probably include 1 or 2 chapters, and or 1 or 2 models discussed under the topics of categorical data analysis. So probably the main aim of today's is hopefully by the end of the sharing, you will take home something knowing what doubly classified model is and find it useful, and you might consider using it in your future analysis. Yeah. So roughly, I'm going to introduce what is square doubly classified tables, what is the aim of doing it, introduce 4 models for doubly classified models, how we're going to apply it, what are the other classified is not going to discuss in this sharing, and the references at the end. So what is a doubly classified model? Doubly classified models are for doubly classified tables. And doubly classified tables belong to a special type called square table. A square table is actually a contingency table that is in n times n. A contingency table is any tables with n times m dimension. So if both row and columns are the same, we call it a square table. If they have the same codes and meanings, we call it a doubly classified table. And doubly classified models is the model to model doubly classified table. So put it very simply. Yeah. So square table, number of rows is equal to columns, double classified table, both row and columns is identically coded with identical meanings in it. So the following is examples of a doubly classified tables. It is a mobility table that is quite frequently used in social science research, where the rows is the son, occupation, status, and the columns is the father, occupation, with the same 4 codes here. And this is a 4 by 4 doubly classified tables with the number of observations shown here about the relation between sons and father. Yeah. So if you so the main aims of doubly classified model is to find an appropriate model that describes the relationship of the cells. Yeah. So if you have a 4 by 4 table, probably it's not too difficult to find the relationships. 2 by 2 is equally easy. Yeah, but you have a 15 by 15 tables, probably you need 255 cells to know their relationship, so that is quite a difficult task to it. So doubly classified models is suitable in this situation. Yeah, so the way of doing it is, for those in statistics probably would know about it, is actually a log linear models that is underlying it. Yeah, the R function to do it is simply doing GLM, stand for generalized linear models. More specifically is Poisson models, we are using it here. Yeah. So it's not a very complicated models. So it's a log linear models using some specification of metrics underlying it. Let's say a log linear model with this form, with a means and a specified of a matrix. In this instance, this matrix will specify the models of a doubly classified models. Yeah, so it normally we refer to a matrix that is of the same dimension to the tables, and from there we generate a doubly classified models. Yeah, I'm going to introduce just 4 models here. So there are more models that is available in the literature. I'll refer to them in the later slides. Right? To start with, complete symmetry models is saying that the cells of 1, 2 is symmetric to, is equally likely to the same as 2, 1. And 3, 1 is equally likely to 1, 3. And the rest of the cells have the same type of properties. That means the cells is equally likely with the diagonal as the reference. And this is, so you can see that the specification of the matrix as the matrix here show that this 2 is equally likely. The one in 3 painted in yellow is also equally likely. So it's not too difficult to specify this particular model called complete symmetry models. And some would prefer to have a hypothesis being stated mathematically. I'll suggest called symbolic tables that I created to say that you look at the tables because they are in table form. So we're analyzing n times n tables. So you can always do something that put in the symbol into the tables, and it will probably more intuitive to readers that's not too comfortable with mathematical expressions. Yeah, so how to do it in R? Next, we refer back to this particular tables, which is a mobility table of sons and fathers with the number of observations on the 4 times 4 tables here. So to specify in R is actually quite straightforward. You just put the corresponding to create a factor, because the G of M read in factors rather than a matrix. So there's a reason for why it's specified as a factor. The specific factor is just give a name to it and put concatenate all this into one columns. And the next, you specify a vectors for the matrix being written into the GLM. So just now we saw the S matrix, which is symmetrical in reference to the diagonal. So this is 2, this is 2, this is 3, this is 3, this is 4, it's 4. It's all symmetric to the diagonal here. So to do that, same thing, create a vectors for S, and that is written here as a 454, but in fact it is stored as a vector. And convert the vectors S into a factor, which is translate that into this format. So for those to do that, it is probably quite intuitive. Yeah. And next, to fix the complete symmetry models using GLM, just put in COMS, which is the name of the vectors for the data, and tutor S, which is the explanatory variables, which is this particular matrix. And then the family is Poisson, because we are running a Poisson models. Yep. And lastly is to evaluate the model fit. A model.summary is written, a book is written for this, so that there's a function called model summary, which will summarize the model the fit statistics for the models. The degree freedom is given. The fit, the G-square is given, the p-value, AIC and BIC. Yeah, so complete symmetry model probably is not too, in reality is not too, does not fit data do not fit very well, because it's a simple models. Yeah, so there are other models that there's available in literature. One of them is called conditional symmetry models. Put it as CS. So what this models means is that the symmetrical cells is in a constant, with a constant terms of gamma. That means the pi ij is equal a constant to pi ji. That means this cells is one constant to the other cells. Cell 1, 2 is a constant to cell 2, 1. So the probability is not, in this instance, this is just 1. Yeah. So to do that, instead of specify a S, we need to include another matrix, is the CS. Yeah. So the S show the symmetry pattern that 2 is here, 4 is there, 9 is here, so in symmetric to the diagonal. While the CS is saying that it's specified in this way. One set on the lower diagonal, one set on the upper diagonal, and one on the diagonal. So more intuitively saying that this set of values is one set which remain the same, and the off diagonal one is a constant is specified by the CS, the symmetric pattern is specified by the S matrix. So it's not too difficult to generate doubly classified models if we know what are the metrics to be specified in order to generate the doubly classified models. Right. So in terms of our in terms of the R program, everything remained the same. The only thing that we have to add, these are the complete symmetry with the data, with the S specifications, and here is the same, the data of the S, but the only thing that we have to add in the CS. So we add in another matrix, a specification, and then we generate the models. So the models here from the data that for the son and the father occupations, the estimated gamma is 0.5. So see it, and the fit here, it shows that the AIC actually is lower for the CS compared to the S. So there's to say that the fit here is better for the CS than the S. So not only that the cells probability can be used for doubly classified models, odds also can be used. By means of odds, that means a probability cells over the other probability cells, if it is the odds. It's the same as you go for horse racing, bet for horse racing, there's the odds. So it's the probability against the other probabilities, right? Yeah, so it can be in this pattern. That means the odds of these two is a constant. Then the next one is another constant, and that is another constant, and that is another constant. It's called odd symmetry model 1. 2 is the other way. That and the odds of this set is the same. The odds of another set is also the same. So the only thing that is need to be specified is specify same thing, the S to show the symmetric pattern for the diagonal in reference, and specify another matrix that is in line with this pattern. Yeah, so the 1 and the 4 here is one set. 1 and the 4 here to one set. And the 3 and the 5 here, and the 3 and the 5 here is another set. Yeah, so there's no reason that we do, yes, 5 minutes, all right. There's no reason that we do not use, we mentioned about this, that diagonal, and we also mentioned about we can use the odds. We can use the diagonal on the other direction. We can fix the center as a point to model doubly classified. Yeah, so we not only can use the odds, the group of odds, the cell probability, groups of cell probability. We can also use odd ratio, which is take account of the 4 cells into account rather than 2 in the instance of odd ratios. And we can combine any of this, also including marginal totals. Yeah, so what we have covered is complete symmetry, condition symmetry with a constant term with the upper and lower diagonal, and the odds is taking the cells probability of 2. We can quasi-symmetry actually is taking the relationship of cells by taking the odds ratio into consideration. So there are lots more of these models, and S-symmetry model is one of them, and there are some other models as well. And there's a book that written on this, Doubly Classified Model with R. If you're interested in it, you can go to these websites. Is the Jupyter notebook that have this, all the notes will be there. And the books also cover modeling strategy, symbolic tables for all the rest of the 44 symbolic tables, models, and how to create this model if you want to create your own models, right? And other references, Goodman is a very good, Goodman's lawyer, and the Zimazawa and the two Japanese statisticians are the experts in these particular areas. So that is the books from Lower, and thank you. Other type examples. Other type examples, is it? Yeah. We mentioned about pairs of matched individual sons and fathers. we can use for inter-rater agreements as well. So if in the study there are two raters, how the rater patterns, if they differ, what is the pattern of the two raters? So one rater is 1 to 5, another one rate to 5. If they're all in agreement, they're all in the diagonal. Yeah, if they are not in agreement, then, and there's a lot of disagreement, you want to know what is the pattern for between rater 1 and 2. That is also another application. Another application is longitudinal study. Let's say you ask the student satisfaction in one time with a scale of 1 to 10, and the second wave you ask the same student, then you can see where's the pattern that is changing. And essential similar variables can be used as well. Let's say you want to know what relationship between the right eyes and left eyes. You can tabulate table and use that models. And the last one is if you want to have skills, let's say you have if a construct, then you have the indicator 1 and indicator 2, you want to know what is their association like. That's also applicable. Yeah, it's just to understand how the relationship of cells for these doubly classified models. Of course, it's a bit limited compared to other type of regression models. Yeah, but if you want if you have any tables, there's n times n tables, you want to know the relationship, and then that is the doubly classified models could probably do the functions.